Okay, so in this video, I want to talk a little bit about conservative vector fields and the fundamental theorem of line integrals. So, oh, come on, go away. Okay, so let's say we are in some situation where we have some vector field, and this is equal to the gradient of some scalar valued function. So in other words, in the language that we've learned so far, we would say that f is a conservative vector field. And let C be a curve. A smooth curve is a curve with smooth parameterization R of t. Okay, then what we know is that the line integral of f over this curve with this parameterization, well, just by definition of what f is, this is going to be equal to the gradient of f dotted with dr. This is just going to be f of r of b minus f of r of a. So to think about why this is true, notice that the gradient of f is just the derivative of f. So really, this is just a statement very similar to the normal fundamental theorem of calculus. And it looks even more like that when you consider that the way we compute this is the integral from t equals a to b of the gradient of f evaluated at r of t dotted with dr. So it's like the variable of integration is r, okay, and then this is f prime. So an antiderivative of f prime is just going to be f. So this is very analogous to the fundamental theorem of calculus. Okay, now one of the things that it tells us is the following. So if f is a vector field, if f is conservative, in other words, f is equal to the gradient of some function, so it's in this situation here. If f is conservative, then the line integral of f over the curve C1 is equal to the line integral of f over the curve C2 whenever the starting points of C1 and C2 are the same, and so are the ending points. Okay, why is that? Well, let's think about this. So let's say that the starting point, so let's say that, let's think about why this is true. So let's say that f is equal to the gradient of some function f. So if f is equal to the gradient of f, and let's say C1 starts at the point x naught, y naught, and ends at x1, y1, then the line integral of f over C1 is just equal to f of x1, y1 minus f of x naught, y naught. Why is that? That's just what this formula here says, because capital F is the gradient of f, and so according to this formula right here, it says that the line integral of f over C1 is just equal to f of the endpoint minus f of the beginning point. And similarly, since C1 and C2 start at the same places, the formula also says that this is the line integral of f over C2 because the start point of C2 is x naught, y naught, and the end point is x1, y1. And so again, just using this formula up here, it says that the integral of f, the line integral of the vector field f over the curve C2 is equal to f of x1, y1 minus f of x0, y0. Okay, so what this tells us is that whenever f is a conservative vector field, then the line integral of f, if you have two curves with the same starting point and initial point, then the two line integrals are equal. So in other words, the path that you take doesn't matter. So if this is x0, y0, and this is x1, y1, and you're integrating f along this path, or you're integrating f along this path, if f is conservative, then the line integral along this path is going to be the same as the line integral along this path, as long as they're both going from the starting point to the ending point. Okay, as long as they're both oriented in this direction. They're both oriented in the same direction, they start from the same point and they end at the same point, then the line integral of f along each of these paths is going to be equal. That's what we mean. When a vector field satisfies that, we say that it is path independent. Okay, so whenever whenever this is true for all paths with the same starting and end point, we say that f is path independent. Okay, and it is a fact that I won't prove, but it's in the book. There's a fact that says the following: f is path independent if and only if f is conservative. In other words, f is equal to the gradient of f for some little f. Okay, so f is path independent if and only if it is the gradient of some function f. In other words, if and only if f is conservative. So f is path independent if and only if f is conservative. And these are the type of vector fields that you are used to seeing in physics. In the next video, we're going to see how we can use these two things to help us compute line integrals.